Was it actually going to come out?
Done, I think. Okay, so our next speaker is Ravi Kannan, and his topic is learning latent polytopes.
Yeah, thanks. Yeah, this is learning latent polytopes via subset smoothing. I'll tell you what subset smoothing is. And it's joint work with Chiranjib, Bhattacharyya, and Amit Kumar, as I note on the abstract. So first, the problem is that there is a latent polytope. Latent means it's not given, so you have to find it. It's a polytope in d-dimensional space. So I guess everyone knows what a polytope is. It's just half spaces, and it's the intersection of half spaces, right? Closed set. So you're given n data points, a1 through an. They're generated by a process that is a latent process. The process is not given to you. You generate points in the polytope. I'll have a picture in the next slide, which might be more useful. But we generate latent points B1 through Bn in the polytope and generate perturbations, how we perturb each of them, C1 through Cn. Also, all D vectors. These are independent, stochastically independent, zero mean vectors, random vectors, and you add them. So you can think of Ci for this talk, for all the intuition, as just Gaussian with spherical Gaussians. Okay? And what you see, what is output to the algorithm is Ai, which is Bi plus Ci. Okay. So the learning problem is, given these Ai, find K approximately. Its vertices perhaps, or some description of K. So in the example, Cj has d dimensions. Each has standard deviation sigma, so it has the lengths of those vectors are root d times sigma. But we generally want the error in approximating K to be much smaller. So all of this is captured by one little picture here. So here's the triangle is a K, okay, and the points you see, or the x's, or perturbed points, schematically they should be actually far away, but I've made them as far away as possible here. None of them lies, in particular, none of them lies in K. So you're given a bunch of points far away from K, and you're asked to find K. Okay. None of them lies in K because K is usually smaller than D, so it's a low-dimensional subspace, and none of them will lie in there. They're all far away. So examples. So quite a lot of hidden variable problems, quite a number of invariable problems are of this nature. These are special. They are special cases. So latent variable models in machine learning, I'm sure many or all of you are familiar with that, but I'll just give you the examples without describing them exactly. So Gaussian mixture models are special cases. I said soft mixture, and I will tell you what soft is. Soft just means that every point belongs partially to different clusters. Okay. Topic models, LDA is an example where, in Gaussian mixtures, the vertices of K are the means of the components, as I'll explain a little bit later. In topic models, the topic vectors are components. If you're not familiar with any of these models, don't worry, they don't matter. All that matters is the geometric problem that's been abstracted out. Stochastic block models, mixed membership community models, these are generalizations of stochastic block models. Again, it doesn't matter if you don't know what they are. We describe only the first example. So you're familiar with Gaussian mixture models where there are components. Here also there are components. The components are standard Gaussians, each centered at some point in K. There are little k different Gaussian components, and in big K the points are located, the means are located. Okay. So you the ith point doesn't belong to one clustering as in normal clustering, but picks a soft cluster. That is, it picks a BI belonging to K, so which is a convex combination of the means. K is vertices of the means, so it's convex combination of the means. And the CI are chosen this way, and you still see AI equals BI plus CI. Okay. So in Gaussian mixture, if Gaussian mixture models are the example, what you're trying to learn, the problem is only the means of the components. And it's easy to see that once you have them, then you have clustering possibilities are easier. So in Gaussian mixture models, if I give you means, everything is given. And that's all you're seeking to find here. For hard clusters, so for hard clusters is normal clustering, where everybody belongs to one point, one cluster, one component, sorry. So the BI can be thought of as one of the means instead of a convex combination of the means. Projection to the principal component analysis subspace, if you're familiar with that, that's fine. Even if you're not, that doesn't matter very much what PCA is. Subspace reduces the signal-to-noise ratio. That the first provable result is due to Santosh and one of his students, and there are many results since then. Subset smoothing is another way to reduce noise. So projection to the PCA subspace improves signal-to-noise ratio. Subset smoothing we'll see what it is, and we'll see that it's another way to reduce noise, perhaps in addition to the kit.
May I ask a quick question?
Yeah.
The AIs are given and the BIs are to be found. Is that equation the definition of CI then?
Yes. So BI, you need not find the BI. I'm only looking for the polytope K in which BI are drawn from.
Okay, yes, but I was confused about the meaning of CI there.
CI is stochastic random vector, also latent, of course, because AI is given, BI is latent, CI is latent. So you can think of it as noise, but noise is a misnomer because in the Gaussian mixture model, there's really a displacement.
Ravi, I guess in this slide, the CI is normal from, it's normal to origin, right? Or because then you're adding it to BI later, or?
I'm sorry, you're right. CI is, sorry, maybe that's the question. This should be 0. I made a mistake there that I added the BI already, so this should be 0. Okay, now we come to subset smoothing. So far, sort of intro. So I want to define something called the subset smooth polytope K prime from K. So we are going to assume that to each vertex of K, there are some number of BI close to the vertex. If you're familiar with LDA models, for instance, or any of those models, there's a Dirichlet prior on the BI, and that ensures, that implies this. So it's not really an assumption, it's actually a fact. I won't go into the Dirichlet prior and so on. You are familiar, that's good, otherwise it doesn't matter. So otherwise it's just an assumption. Then first of all, convex hull of BI is close to K. So the picture is this is K. So we assumed at least one BI. In fact, we assumed many BI are close to this. These are BI. That means the convex hull of those BIs is close to K, and therefore the convex hull of all BIs is close to K.
How should I think of the distance between polytopes?
Distance?
Like, what's your notion of close?
Yeah, close is sigma. So I'm not going to be precise with the details in the first part of the talk. In the second part I will be. But the closeness is sigma, roughly to think about. Some K factors times sigma, not D, no D factors. Okay, so sorry about the details of the technical details I didn't put in, but I'm hoping to give you an idea, intuitive idea of the main tools. Okay. The average of the m data points, the AI with the latent points close to BI is close to a vertex of K, is also close to the vertex. That's what we are saying here. The average of these guys are close to the vertex. So now, we don't know which subsets of points, which subsets of AI came from things close to the vertex. We don't know that. If we knew that, we would have solved the problem. So we are going to do the convex hull of the averages of all M subsets. Again, there'll be a picture which will hopefully clarify. So I don't know which subsets are good. I'm going to take all subsets of that cardinality and take the averages and take the convex hull. The average reduces the variance, as always. And that's the purpose of taking the average. But if I do that, I'm sunk, because I'm trying to develop polynomial time algorithms. K prime is exponential sized as I've described it. Okay, so that seems to be a basic problem, because I'm going to deal with K prime, and that's my prime object. But there's a savior here. That's a qualification on the but, is K prime has a polynomial time optimization oracle. So if I want a linear function optimized over K prime, I can do that in polynomial time, because I just find the M maximum C dot AIs and take them. That should be the best. Okay? So that simple fact that there is a polynomial time oracle should give you an idea of the convex geometry. That's an important tool to get a lot of algorithms. Before that, a picture. Here's the original triangle. Here are the points AI, far away from the triangle. Here I've taken averages of, I guess, 3 or 4. M is 3 or 4. I don't know what M is. But they're all pretty close, as the picture shows. Just because the variance is reduced, that's all.
But could you do averages of averages in order to do this efficiently? So it's just kind of like a boosting of averaging type thing?
So as you take averages, the thing shrinks, the convex hull of the point.
You're right.
And after a while, it's going to shrink away from the vertex. So if I take the overall average, for example, then it'll be just the median.
Yeah.
So you don't want to do too much averaging. You want to average only with small sets.
I believe that. I'm still kind of wondering if computationally you can do something where you do a sequence of a small number of averages rather than an average over larger sets.
Okay, so if you do averages over very small sets, then there'll be just, let's say 1, for example. If I average every single point, I'll just get this thing back, which
Let's
is...
do 2.
And so let's say 2. You still will be bigger than the polytope.
Let's do 2 twice. Let's
Two.
do 2 and then do 2 on the result.
Okay, let's see. I don't know. I can't average so fast, but
Okay.
yeah, that's a good question. I don't know what that. Yeah.
So I guess all averages of all M subsets, you're doing some correlation of some kind, right? Like, or your new samples are correlated in a useful way.
So in fact, the averages are small follows from random matrix theory, which uses the independence rather than the correlation of the points. So even though they are very far, if I take the average of a bunch of them, it'll shrink for one set that's just raw statistics. But I want every set to behave properly.
Every subset.
Every subset of M things. And that happens, you don't do union bound, but it happens because of random matrix theory. Okay? So if I had all the averages written down, I found the polytope, at least in this picture. And that's going to be the intuition, right? So use of optimization oracle to find K prime. We prove the convex hull of points found by an optimization oracle polynomially many times. So I take random vectors and maximize those vectors over K prime because I have the oracle. and the combination of those does the job without being precise. Again, I'll have a picture. Further, the k vertices of k can be approximately found from the optimal points. This is a connection to Avram. The second part was previously done by Avram and co-authors, actually a nice paper with just some other things as well. They were motivated by something different, but they did this. Okay, so here is a simple picture description of the algorithm that I'm using. I'm sitting at the origin, let's say, or let's say the origin is inside the K. I'm sitting at the origin, and I'm shooting random rays, and for each ray, I find the maximum of that C, let's call it, the vector C dot x over the polytope. So this ray, the maximum is attained in this vertex or that vertex. For this ray, the maximum is attained at that vertex. And for this ray, maybe one of these. And this ray gets you this, and this ray gets you this. So the point is, we got all three vertices occurring as the maximum for some ray. And therefore, if I take all the optimum, all the maxima, and take the convex hull, I would get all of the polytope. Okay. Okay. How do we prove this? Okay. So part one, I'm trying to prove part one. The convex hull of the points gives you all of k prime, and k prime and k are almost the same. And this has to do with separating hyperplanes. So I'm going to introduce, if you can turn off all the stuff I said. If this is a self-contained bit about separating hyperplanes, convex geometry, right? So you know the separating hyperplane theorem. Recall that it says that if I have a closed convex set, polytope is a closed convex set, and a vector, there's a point x not in the set, there's a vector u that separates them, that puts x on one side, the entire polytope on the other side. So u dot x is greater than the maximum u dot y belonging to k. Okay, so we asked the question, and I won't necessarily connect with the previous stuff, but it connected. K is a closed convex set, and x doesn't belong to k. Does a random u separate x from k with what probability? So I'd like this to solve the other problem in a way. I won't go into details. Okay, so the probability is positive. That's easy to see from the classical theorem. But is there a better bound, at least a 1 over poly lower bound on the probability? That's not so in general. So here's an example. I'm sitting in d dimensions. The convex set K is in d minus 1 dimensions. It's a unit sphere, except x1 is 0. It's in 1 dimension lower. And x is a point which is in that dimension, actually, so 1, 0, 0. X doesn't belong to K, obviously. But if you take a random u, the max over K is almost 1, whereas u dot x is only 1 over root t. So just 2 minutes of thinking convinces you that a random u will only work with very small, exponentially small probability. So the answer to that general question, closed convex set, does a random u separate? The answer is no, it doesn't do it with very good probability at all, in general.
Does it depend on the margin between the point and the set?
The what?
The
On
distance.
the margin, the distance.
Yeah.
Okay. Good enough.
Sorry. It does, I'll come to it. So it is a function of the distance, as you can imagine. If a point is very close to the convex set, random one won't work. If it's not, it'll work. But it's a complicated function of the distance. No, not complicated, but it's an exponential function of the distance. So, Okay, example 2 is a simplex in one low-dimensional space. Again, y1 is 0, y2 through yd sum to less than or equal to 1, that's simplex, and then the point 1, 0, 0. And now you can see that any u that has u1 as the largest component separates these two. Okay? So the probability that u has the largest component as u1 is 1 over d, so that's 1 over poly. So with 1 over poly probability, you do get separation if it's a simplex. So if it's a simplex, you get separation. If it's a ball, you don't get separation. These two examples will give you the theorem, not the proof, but the theorem statement. So it's a polytope with k vertices and diameter d. X is a point at distance omega of d, constant factor times d from k. Then with probability 1 over poly, a random vector in the space spanned by k minus k union x separates x from k by at least d over root k. So again, a picture. So this is x. This is the polytope k. And the distance that it separates by is omega of d. D is the diameter. Diameter is this red line, is the largest distance between 2 points and k. That's d. This is some constant factor times d. And the theorem says if I pick a random u, so this is my random u, then the distance along u between these two is d over root d, big D over root d. So it should be root d, sorry. And that root d is reminiscent of Johnson-Lindenstrauss. It is actually, so it cannot be improved just because Johnson-Lindenstrauss is tight. So is the picture clear? So I don't have to know k, I don't have to know x. I just randomly pick a u, and with high probability, it's a separating. If it's not there, then it's separating. If x is not in k, then it's separating, provided it's at reasonable distance. Now, to answer your question, if the distance is less than this, it still separates with the probability. The probability is exponentially dependent on the distance.
So another question. So if I know x, then I can make, if I choose a random u that goes through x,
Yeah.
then my probability of separating is much higher, right?
No, if I know x, if it's close in
No,
distance.
and I change and force u to go through x.
Yeah, that's right. But
Then,
you're worried about the right-hand side.
yeah.
Yeah, the right-hand side I finessed that by just saying max over k and x. So the u going through x gets the maximum
Okay.
separation. Okay, so let's see. So that this theorem said if x is a point at distance this, then it's separated. It's a more general theorem is true. If k1, k2 or two polytopes, each with k vertices and diameter d, and the polytopes are separated by a distance omega of d, then with probability at least the same conclusion. So, but this is more general because k2 was a single point there, and now it's a whole polytope. Separates k1 and k2 by at least this distance. Again, this should be root d. So actually, I'm at my last slide. This forward doesn't get you anything new. So I'm done, but is there any other questions?
Is the dependence on k required? Could you reduce it to some other function of the dimension?
No, the dependence on k seems needed. Because if you think of a sphere, it's got k exponentially large. and therefore it should depend, the separation, you are not able to do the sphere, so.
So you get, you get the simplex as one example, and then the d minus one dimensional ball is another, and that one's defined. So by k for the ball is infinite or extremely large, and that's what's making this difference.
Yeah.
But I guess what I'm confused about is you can put a box around the ball,
Yeah.
and that's defined now by many fewer points.
Right, but then the distance of the separation, distance x is far away from this will go down.
You're saying that now,
So you're saying if x is far away from the cube, not the cube is the wrong object, octahedron, right? Cube has too many vertices.
oh, I see, the cube does have a lot of vertices.
Yeah.
doesn't it? Okay, so I can't just, because it's a small number of facets, but a large number of
Vertices.
vertices. I see, so that's,
For the octahedron, this theorem is true.
I see.
For the cube, it's not.
You're saying really then all that matters is, you're just trying to separate one point from a set of other points. I mean, I can think of it like that.
Yeah. So not one point from, it's not enough to separate the point from all the vertices, because the closest point to this point may be in the convex hull, may not be vertices. So it would be it's a simpler problem to say, I have a plane which puts all the vertices on one side and this on the other side. That's not enough. Yes.
Are you motivated by specific examples?
Yeah, so I am motivated by examples where the number of vertices is small. So that's a good question. So in all the models, like topic modeling, the number of topics is always thought to be smaller than number of dimensions. So we are interested in such objects, small number of vertices.
So, Ravi, could you explain again why sort of separating the, looking at just the vertices of the polytope are not enough?
Because the closest point, so all the vertices might be on the other side. Sorry. You have to separate all the vertices. Okay, that's yeah. Sorry, I backtrack. You're right. You have to separate. One thing has to separate all the vertices from X. Yeah, then it's fine. But the point is, a union bound won't do. That you say Johnson-Lindström or even simple thing. This vertex is separated from this. This is separated with some probability. If you add up the failure probabilities, you get more than one, right? So.
I don't have the sense of how this relates to the volume of the sphere versus the simplex.
Yeah, simplex has much smaller, exponentially smaller volume, right?
Yeah.
So, in a sense, there's no magic. So you can ask if the volume if they give you a high volume object, is it still separated?
No, but the volume is scalable. Just change your metric and the volume goes up. Just blow it up.
I'm thinking volume relative to distance, right? Like the volume of the object versus the relative to the distance to the point.
Yeah. So I don't know a clean term. So it's possibly true that as the volume increases for one object, as you blow it up, the separation distance goes down. But I don't know a clean theorem which says if the volume is such and such, and so this is clean. If the distance is such and such, then there is a separating randomized thing. I'm really glad that we are making up the time deadline. Thanks.
So, but volume and dimension.